It's a lot of homework. A lot of problems.
Yeah, cause there's so many data points every single time, so.
You know, these-
Now, these box plots and percentiles are not a big deal. Nothing else in the course builds on that,
Okay.
so we're not gonna worry too much about getting them exactly right. Z-scores are a big deal. Be sure you can do
I'm
Z-scores.
not balling it, huh?
Yeah. I think it's more this way. But see, then when I did this one, I actually counted them out. I counted each one so that I can make it accurate.
Hey guys,
I just want my
I'm gonna fix mine now. Yay.
So my ruler, I want
Okay, now these
exact
whiteboards will
measurements.
not be erased, they'll be here till 10 o'clock.
Oh, that's
If
okay.
you want to digest them.
Here you go.
That's not marker.
For the moment, we can slide them back into the barn behind
Can I make
Tony's chair there. You want to do one with me?
that? Sorry.
Oh, take your time. No, I didn't, take your time, dear.
Okay.
So we can stow the
Are we
boards
good?
and
Okay,
look at them after class if you care to. So a Purple Heart for the people that worked through their break.
Everybody looking. I have room.
Okay, we'll resume now. And I need to remind you that when we come in 48 hours, first thing we're going to do is we're going to put A4 on the whiteboards. Going to go over assignment A4, and then we're going to test on A1 through A4. That's our agenda for next class on Thursday. And every test problem will be selected from the homework. So I want to be sure you can do the homework problems. A suggested way to do the homework problems is to do them all on blank paper, crumple up the paper, throw it away. Pick up new paper. Do this 7 times. Internalize. Height leads to high scores. So don't worry about turning pages in the text or understanding material, because it is unknown what the problems are going to be, so it's an execution situation. You want to be sure you can do those problems. That's what it's all about. Good. Now, on this assignment A4, you're asked to do some problems on page 180 and 181 of the Xerox pages near the end. Some of those problems can't be read due to the poor Xeroxing, and don't worry, just don't do the ones you can't read. That's okay. Now I'm going to continue with the remaining 2 sections of tonight's material, 11.2 and 11.3 in this handout in presentation mode. And I need to remind you what we're doing, and that is we're learning how to count. We're learning how to count because with classical probability, the probability of A is given as, Tony, what's the probability of A given as in classical probability?
The number of table matches over the number of possible.
That's great. That's great that you knew that. This is exceedingly important. But in order to write a number for the numerator and to write a number for the denominator, you have to count. So we're pausing now in our development of probability and learning some shortcuts for counting. Now we've learned the fundamental rule of counting, that if you have a 3-digit license plate, 987, then that's 10 selections for the first, times 9 selections, times 10 selections for the second, times 10 selections for the third. But now suppose we live in a different state which has a stipulation that license plates, the digits cannot be duplicated. For example, a license plate such as 991 is disallowed because it has 2 9s. Each number must be different from the other 2. Exactly. Tell us why you thought about that. How many choices for the first? 10. But for those 10, how many choices for the second? There's only 9 left, agreed? And now how many choices for the third? 8. Now what we're doing is selecting 3 numbers out of a set of 10. This is the number of different license plates you can get. Now, when there was no restriction, you got 10 cubed, but with this additional restriction, you get 90 times 8, which is 720, instead of 1,000. So let's take another real-life situation. Suppose I'm going to have the members of this class line up at the door, okay? And I'm going to select 4 people to line up at the door. How many different lines can I make? Well, how many choices do we have for the first person that goes up there? 6. Now, how many choices for the second person? And how many choices for the third person? How many choices for the last person? 3. So that's the number of lines that we can get at the door. Now, what we have done is select a selection of 4 from a pool of 6, and that is known as P64, where we have a pool of 6 and we are selecting 4. In general, it's known as PNR, where you have a pool of N and you're selecting R. Now, the reason I'm forming this line of people at the door is we have an enemy shooter outside the door. First person through the door is going to die, sacrifice. Second person, 50-50 chance. Third person is going to take out the shooter. The fourth person is going to video the corpse. Does it make any difference which position in the line you're in?
Yes.
Seriously, right? So this is a case where order matters. The order of selection matters. The first person selected has a very different fate than the last person selected. So when you're making a permutation where the order of selection matters, a selection where the order of selection matters is called a permutation. So let's take another one. I'm going to form a 3-person government. A 3-person government. First person selected is going to be president. Second person selected is going to be vice president. Third person is going to be secretary. So out of these 6 people, how many different 3-person governments can I form? 6 times what? Times what?
120.
So how'd you get it? 6 times? 6 times what? I can't say it.
There's a fancy button on my calculator that does it for me.
You didn't say that. Nobody heard that. Put that down, don't say that ever again. 6 times 5 times 4.
So 120.
See what you've done?
So,
See what you've done? Okay, now, this is the logic behind a permutation. And that is the number of ways you can select the first one times the number of ways you can select the second one times the number of ways you can select the third one on down. And you see, you can select each succeeding member a fewer number of times because the pool is shrinking. But the fundamental tenet of a permutation is that if you have a different order of selection, it is a different permutation. If I have Freddie as the lead through the door, let's put Hannah as a lead through the door, Freddie second, Kaylee third, and Casey fourth, is that a different selection than if we put Kaylee first, Casey second, Hannah third, and Freddie last? That's a very different selection, agreed? So if in your selection, the order of selection leads to a different selection, then it's called a permutation. Good. Now, there are certain selections where the order does not matter. If you're making a selection where the order does not matter, it's called a combination. Now, what I'm going to ask now is how many different teams of 2, how many different teams of 2 can I select from this class of 6 to go out to the perimeter? Now, these team of 2, they're gonna have equal rank. There's no difference between the two. They're gonna be doing the same things. One's not in charge. They're absolutely equal. So it doesn't make any difference whether you were selected first or second, it's the same team. If I choose Freddie first and Kaylee second, it's the same team as if I choose Kaylee first and Freddie second. It's the same team. They're going out equal. So we have a team that we're selecting where order of selection does not matter. So how many different teams of 2 can we go out to the perimeter of the base in a suicide mission, take out the enemy and save all the rest of us on the base? How many teams of 2 can we make from this pool of 6? Yes, but the way that we get it, let's go through the steps. The way that we get it is first we pretend for a moment that order does matter, that the first person selected is going to be in charge or something like that. So now how many teams of 2 can I get if I select them on the basis that order does matter? How many teams of 2 from this 6? How many choices for the first? 6. How many choices for the second? 5. So you can get 6 times 5 teams of 2. But order does not matter. So let's do that slightly different. Suppose that I'm choosing a 2-person government. First person's president, second person's vice president. How many governments can I choose from this class? 6 times 5. If I relax the requirement that order matters, then I have chosen each government 2 times too many. For example, let's look at the team of Freddie and Kaylee. If they're a team where order does not matter, then if I select them as a government where order did matter, I got 30, agreed? But I selected one government with Freddie as president and Kaylee as vice president, agreed? But didn't I select a different government with Kaylee as president and Freddie as vice president? But those 2 selections, if I relax the requirement that order matters, aren't they exactly the same team? So now I've counted that team twice too many times. So I have to divide by the number of overcountings that I made of that team. So I have to divide that by 2. And that tells me how many teams of 2 I can get when order doesn't matter. First I pretend that order does matter. I get 30. Then I divide by the number of overcountings that I made. How many teams did I count the same? I counted that team twice, agreed? So I have to divide by 2. So the ultimate answer is how many? 15. Now let's try a 3-person government. Suppose that I'm going to select a 3-person government. Then I want to ask how many 3-person governments can I form from this group of 6? And the answer is how many? 6 times president, vice president, and dog catcher. Okay? 6 times 5 times 4. Number of different governments where order of selection matters. Now, if I'm going to relax the requirement that one of those governments of the same 3 people is different from another one, in other words, they're a team of 3, democratic, no rank, then how many times have I counted the same government? I have to divide by the number of times I counted the same government. So let's see how many times I counted the same government. Once, with Freddie as president. Freddie, could you stand up? Freddie as president. Now with Freddie as president, I could have had Kaylee as vice president and Tony as dog catcher, true? That's once. Or I could have had Tony as vice president and Kaylee as dog catcher. That's twice, agreed? 2 governors, thank you. Great job. Kaylee, could you be our president? Now with Kaylee as president, I could have a government with Tony as vice president and Freddie as dog catcher. Or with Kaylee as president, I could have Tony as vice president, Freddie as vice president and Tony as dog catcher, agreed? That's 4 so far. Thank you, great job. Tony, As Tony is president, how many governments can we form? Two, for a total of how many? 6. Now, this team of 3, if I say the order does not matter, then I counted that team 6 times too many. So I have to divide by the number of overcountings that I did. And I get the number of times I selected that team when order didn't matter, because I selected it 6 times. So this is how you get the number of teams that you can form from a pool. First you get the number of selections based that order does matter, and you divide by the number of times you overcounted any selection. Now I'm going to show you a simple way to calculate the denominator. Looking at this group of 3, I want to know how many governments I could have formed from that group of 3. I answer the question this way. Of the group of 3, how many choices do I have for president? 3. Now for each one of those choices, how many choices for vice president remain? 2. And then for each one of those 2, how many choices for dog catcher remain? 1. So you calculate that as 3 times 2 times 1 to get the overcountings. Now let's extend that to make it clear. Let's have a 4-person government. Steffi's going to be in there also. We're going to have dog catcher. So how many 4-person governments can we form? 6 times 5 times 4 times 3, agreed? But we have overcounted. Now, so out of this 4-person pool that we chose our government from, how many choices did we have for president? 4. And that left how many choices for vice president? 3. And how many choices for dog catcher and how many choices for secretary? So this counting, where order does not matter, is known as a combination. And this is a combination of 6 things selecting 3. This is a combination of 4 things, 6 things selecting 4. And in general, it's n things selecting R, a combination. Now, the masochistic amongst you, I got your attention. The masochistics among you will evaluate this fraction by multiplying across the top, then multiplying across the bottom and dividing. How many are ready to do it that way? Now, the opportunistic among you will first look for any possible cancellations between anything on the bottom and anything on the top. First, let's do it just straight across the top. 6 times 5 times 4 is 120, divided by the bottom, so we get an answer of 20. Now let's try to be optimistic and do any cancellations that we can. The 3 into the 6 is 2, and the 2 and the 2 are gone, and we have 5 times 4, and we get the 20 in one step. So cancel anything on the top with anything on the bottom before you do the multiplication. Now you follow that rule, what things on the bottom can cancel with what things on the top, and leaves what for a final answer. Okay? I suggest the 4s can cancel, I suggest the 3s can cancel, and the 2 can go into the 6 3 times for a final answer of 15. So cancel anything on the top with anything on the bottom. So now we have achieved a logical understanding of what it is that we mean by a permutation and what it is we mean by a combination. So let's review. A permutation of 5 things, 3 at a time. We're going to start with 5 and we're going to write 3 numbers. That's how we calculate it. A combination of 5 things, 3 at a time. We're going to do the same thing as a permutation. We're going to start with 5, we're going to write 3 numbers, and then at the bottom we're going to start with 3 and go down to 1. So now I want you to tell me, what is P11 for? It's going to be 11 times 10 times 9 times 8 for a final answer of what?
11,920.
11,120.
920. 7,920.
Okay, now, C11.4 is gonna have the same numerator, 11 times 10 times 9 times 8, but what is it we write in the denominator to divide out the overcounting? We start with what number? 4 and go down to 1. So after we do all the cancellations and then we do the subsequent arithmetic, we get what number? Well, it's the above number divided by 24. So it's going to be 3, 1,
330.
sorry?
330.
330. Now, there are far fewer combinations than there were permutations. Does that make sense to you? Because in a permutation, the order of selection mattered. So you got a lot of selections that were really the same membership, the same members. So now you suddenly say that the order of selection didn't matter, then all of those selections coalesce, collapse into one selection. So there are far fewer selections when the order doesn't matter. So here we have a permutation and here we have a combination. Now which is the one that applies when order doesn't matter?
Combination.
Which is the one that applies when order does matter? Okay, now I have 9 books. I'm going to arrange them on my shelf. How many different arrangements of my 9 books on my shelf can I make?
72.
Too quick. First, is this a permutation or combination?
Combination.
That's right, permutation. If the calculus book is first, the philosophy book is second, and my friend's photographs is third on down the line, is that a different arrangement than if my friend's book is first and the calculus book is second? Does the order of that I stack those books on the shelf produce a different arrangement? Or not? It is a permutation, agreed? It's a permutation. Okay. So, let's do some problems. So let's go to page, in your handout, the page in the handout, known as 613. 613. This is usually the hardest part of the evening, finding the right page in his handouts. So, Haley, could you read problem 1 to us?
6 performers are to present their comedy acts on a weekend evening at a comedy club. How many different
Your answer is? Write it out. Okay, the answer is, would it be 6 times 5 times 4 times 3 times 2 times 1? A much harder problem, number 2. So Stephanie, how would you do number 2? How many choices for the lead singer, the first one out?
6. No, 5.
And how many for the following?
4.
Okay, so it's 5 times 4 times 3 times 2 times 1. Now this author gets a little bit tricky.
So then it would be divided by.
No division, because each one is a different program, isn't it?
Okay.
It's a different program. The order of appearance makes it a different program. So it's not a team, it's a government. Order matters. How many different programs are possible? But now the author gets very tricky. He does this when he gets up in a bad mood in the morning. he puts in a problem like this, and then he feels much better. Let's go to number 12. A camp counselor and 6 campers are to be seated along a picnic bench. In how many ways can this be done if the counselor must be seated in the middle and a camper who has a tendency to engage in food fights must sit to the camper's immediate left? Answer to the problem is, Casey? Hannah, answer to the problem is,
360.
keep working. I don't accept 360. A graph, a drawing helps on this. Okay, let me give a drawing on the board. So we have these 7 seats. And we have these 7 campers. 1, 2, 3, 4, 5, 6, 7, including the counselor, agreed? Now, this guy has to sit here, in the center, agreed? Now this bad guy has to sit on his immediate left. So how many seats are left? Right, 5 seats are left. How many campers are left? 5. So how many different ways can you sit 5 campers into 5 seats?
5 times 4 times 3.
5 times 4 times 3 times 2 times 1. Because for this seat you have how many choices of campers? 5. For this seat, how many are left?
4.
This seat, these are filled, they don't count, 2 and 1. Tricky, yeah. But he smiles, he smiles, okay. Yeah, he does things like that.
Thank you for picking this one.
So now let's go to page 619. Page 619. Number 1, I want somebody to tell me if it's a combination or permutation. So, page 619, number 1. Stephanie, is number 1 a combination or a permutation? Want a coin to toss?
It's a permutation.
How many support permutation? Okay, give your argument for permutation.
Because it doesn't say the order matters, there's the two, right?
You're saying that order does matter.
Oh, no, I guess it doesn't, so it's combination.
So order doesn't matter, she just had them backwards.
I'm sorry.
Order does not matter, agreed? Those 6 are the same 6, no matter who was chosen first, second, third, or fourth, fifth, or 6th. Number 2, Tony. Permutation or combination? Permutation. It makes a big difference whether you win first prize or third prize, agreed? Freddie. 3, permutation or combination?
Permutation?
Yeah.
No repetition is allowed?
Very good insight, nails it. And Hannah, number 4,
Permutation.
3 winning tickets. Each prize is 500. How much money do you win if you're the first selectee?
That is a combination.
Yeah, because the first one wins 500, the third one also wins 500, agreed? Same. Okay, now I'm going to give you a real life experience. How many of you have opened a combination lock? Raise your hand. Stephanie, combination lock?
Yes, sir.
How you do it? You dial, you get to the first number, then you dial back second number, then you dial back to the third number. Okay? Now my question is a combination lock correctly named? Does the order in which you use those 3 numbers make a difference?
Yes.
If you use those 3 numbers out of order, does the lock open? So, what should a combination, so Kaylee, we tried to join the class. What should drop the pencil, please. What should a combination lock be called? Right, exactly. So the next time you come across somebody that calls it a combination lock, you just straighten them out. They'll thank you for it, okay?
It actually matters how many times you.
That
turn it.
too, it's even more complicated, it's a mess. Okay, now that we have understood what we mean by permutation, and we've understood what we mean by combination, so what we understand, what we mean by permutation is that we start with this number and we write that many numbers. What we mean by combination is that the numerator is the same. That we start with this number and we write that many numbers. And then on the bottom, we divide by the overcounting, we start with that number and we go down to 1. So this is a logical derivation and meaning of what permutation and combination are. Now that we logically understand their content, then, okay, I need to say one more time. I've made it a rule in here that the only thing we do during class is class. And we don't do homework ahead or homework behind or aside stuff, because we need your energy in here to bounce off each other and become amplified. Now that we've understood this, I'm going to teach you an arithmetic operation by which you can do the calculation in an alternate way. But it's nothing to do with what is the meaning of permutation, the meaning of combination. It's just an arithmetic operation that permits you to arrive at the result in a slightly different way. So I'm going to introduce a new arithmetic operation to you called a factorial. And it's defined as this: 5 factorial is equal to 5 times 4 times 3 times 2 times 1. That's the definition of 5 factorial. So what number does it turn out to be? 120, good. Now I get tired of writing 5 factorial, so we've all agreed to abbreviate it with an exclamation point, which is an obvious label for factorial. So 5 factorial is 5 times 4 times 3 times 2 times 1. So what is 4 factorial? 4 times 3 times 2 times 1. And indeed, what number does that come out to be? 24. And what number does 3 factorial come out to be? 6. And 2 factorial is equal to 2. And 1 factorial is equal to 1. And 0 factorial is equal to 1. Okay. Now, factorial is used so frequently that your calculator has a factorial key. One of the things you want to do tonight is to locate it and be able to use it. So I want you to be sure you know how to use it by doing something simple that you already know the answer to, and I want you to get your calculator to tell you that 5 factorial is equal to 120.
Right now?
Yes. Right in real time in this class. Okay? Did you get your calculator to tell you 5 factorial equals 120? It's usually an exclamation point or the letter N with an exclamation point. Exclamation point. Okay, good. Now use your calculator to tell me what 8 factorial is.
40,320.
Agreed? Ready? 8 factorial is that? 40,000?
I'm still trying to find this one here.
BRB.
We do have to know how to do this. No, please do.
That's it.
Enter.
Oh, shit. And then,
Enter again.
Oh, I got it. Woohoo. Fancy,
so they
fancy.
shift this and then just put 5 in?
Okay, so there is,
So
the number
the
you want to
probability
put
of
in.
mine, actually.
hit probability or
Shift, and then this one?
Okay.
So that's it? Okay. So number first, shift, then exclamation. Okay, I got it.
Okay, now, it's ridiculous for us to say that 0 factorial is equal to 1, because we're saying start with 0 and count down to 1. Well, you can't start with 0 and count down to 1. So since it's ridiculous, we're free to define it to mean anything we want. And we will arbitrarily define that 0 factorial is equal to 1. Don't look for any logic. There is no logic. Don't look for it to make sense. It doesn't make sense. But is your calculator in on the agreement? Ask your calculator what 0 factorial is. Your calculator is in on the agreement. 0 factorial is agreed upon to be 1. So now please tell me, is this true? 5 factorial equals 5 times 4 factorial. Just look at it on the board. Well, 5 factorial is equal to 5 times 4 times 3 times 2 times 1. Now this is equal to 5. Now what's 4 factorial? So they are equal to the same, are they not?
Yeah.
Okay, now, I'm going to ask you to do a calculation for me. I want to know what is 600 factorial divided by 599 factorial. So go ahead and start to punch it in if you want to, or else look at it and be clever. No calculator, no punch in. What's the answer? Well, is not 600 factorial equal to 600 times 599 factorial? Is that not a truth? Well, is that a truth? Well, then let's divide by 599 factorial. Is there anything that will cancel? And what does that leave for the answer? 600. Now, for people that didn't want to think before they jumped, they're going to punch in 600 factorial, if your calculator will do it, which it won't. Then punch in 599 factorial, which your calculator also won't do, and then do the division. Or you can just think a little bit. So let's have your choice of whether you want to plunge or think. So let's go back to page 613 and turn the page to 614. Now, I'm going to do number 13. 2 ways. 9 factorial over 6 factorial. Okay, can someone tell me what 9 factorial is? Punch it in.
362,880.
800 what?
80.
Okay, what's 6 factorial 720? I know that one. Okay, now do this division, tell me the answer.
504.
Okay, now an alternate way to do the problem is this is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 on the top, and what is on the bottom? 6 times 5 times 4 times 3 times 2 times 1. Now before I do the multiplication, do you see any cancellation that might be able to be
6
done?
on down.
Now that leaves a much simpler multiplication. And if you do that simpler multiplication, what number do you get? 504, your choice. I strongly suggest that you write out factorials and look for cancellations before you hit the multiplication key. Okay? Now, the same thing could be done, number 14. 12 factorial over 10 factorial. 12 factorial over 10 factorial. That's equal to 12 times 11 times 10 factorial over 10 factorial.
It's 132.
So it's equal to 12 times 11, true? And 12 times 11 is 131, true?
32.
132, yeah. Good.
I'll see what you did. You just stop writing when you hit the common same number.
That's right.
You don't have to go any further.
That's right, exactly true. So that's what we do. Now what about number 27? Here you have an order of operation problems. A factorial is basically a multiplication. 12 over 4 is basically a division. So you resolve these from left to right. So what's the answer to 27? First you divide 12 by 4, agreed? Giving you a 3, and 3 factorial is 6. End of problem. Easy. Okay. Now, how do factorials enter into the calculation for a permutation? Well, we are used to saying that P5, 3 is equal to 5 times 4 times 3. That's its definition. There are 5 choices for the first person in the list, 4 for the second, 3 for the third. But if I take that and multiply it by the number 1, which is 2 times 1 and 2 times 1, did I multiply the top and the bottom by the same thing? Therefore, I haven't changed the number, because I multiplied it by the number 1. If you have the number 3/4 and you multiply it by 1, what is that number still? 3/4. So if you take the number 3/4 and you multiply it by 2 over 2, which is just another way of writing 1, it becomes 6 over 8, which is still 3/4. So as long as you multiply a fraction by 1, you haven't changed it. So is this not the number 1? Anything over itself. But now can the top not be written as 5 factorial? And what can the bottom be written as? 2 factorial. So we say that there are 2 ways to write the permutation. It's either 5 times 4 times 3 or 5 factorial over 2 factorial. Now bear in mind that this is not the definition of factorial, this is just an alternate way to make the calculation. This is the definition of factorial. But let's extend it a little bit. If I want to take P7, 5, then what I have to do is 5 factorial, 7 factorial over 7 minus 5 factorial, or 2 factorial. Well, I'm going to write it out so that we see. I'm going to write 7, 4, 7, 4. 7 times 5 times 7 times 6 times 5 times 4. It's getting late. Okay. Now I want to write that in terms of factorials. So I extend the top with a what? And I put the same on the bottom. So that's written as 7 factorial over 7 minus 4 factorial. You see where the 3 came from? It was the difference of the 2 numbers.
Oh, okay.
That's where it comes from. So with that understanding, you can easily do P11, 6. It's going to be 11 factorial over 11 minus 6 factorial. And we're going to write it out, just to be sure that you understand this. This is 11 times 10 times 9 times 8 times 7 times 6, agreed? Now I'm going to extend that out with a 5 factorial. And on the bottom, I have to do the same thing, a 5 factorial. But 5 is another way of saying 11 minus 6. So the general prescription in terms of factorials for a calculation of permutation is it's n factorial over n minus r factorial. And again, bear in mind that this is not the definition of permutation. It's an alternate way to make the calculation. So with that understanding, let's do number 33. Let's do it 2 ways. First, let's do it as to what it actually is, and then let's do it in terms of factorials. So, and what it really is, P96 is 9 times 7 times 9 times 8.
Which number are you on?
I'm number 33, same as my age.
Here.
Oh, it's P9, it's 9P4.
994. How can a 33-year-old not see better? So 9 times 8 times 7 times 6. But in terms of factorials, it's 9 factorial over 9 minus 4 factorial, which is 9 factorial over 5 factorial. So you have your choice of which way to do the calculation. Now, let's go on to combinations. So we turn the page back to 619. And let's see how it plays out. If I have C74, I know that that's a 7 times a 6 times a 5 times a 4. And on the bottom, I start with 4 and I go all the way down. That's the definition of a combination. We've worked it out in terms of overcounting and dividing it out. So let's see what we have to change to put it in terms of factorials. First, this is already a factorial, isn't it? Which one is it? 4 factorial. But now let's extend the top. We're going to do a 3 times a 2 times a 1, and on the bottom a 3 times a 2 times a 1. Oop. So the top is going to become a what? 7 factorial. The 4 factorial is already there. And what's our new entry? 3 factorial. Now, where did the C3 come from? It was 7 minus 4. Okay? So with that understanding, a C8,5 is going to be a 8 factorial over a 5 factorial times an 8 minus 5 factorial, which will be a 3 factorial. So the definition of the factorial way to do it is it's n factorial over r factorial times n minus r factorial. So if you want to do combinations in terms of factorials, then this is the prescription to do it. So on page 619, let's do number 7 both ways. We have C95 is equal to 9 times 8 times 7 times 6 times 5. In terms of factorials, C95 is equal to 9 factorial over 5 factorial times 4 factorial. So you can write these numbers down, or now you can calculate them. And no matter how you do it, you will get the same number. C n r is equal to n factorial over r factorial times n minus r factorial. So in your handout, that definition is at the top of 619. The top of 619. Now, of course, this handout is our textbook for this week. So read the what? Before you do the problems, you have to read the handout. Do the examples. Now, there's not time for me to present all the topics. So you will find at least one topic when you read it that I didn't have time to present. So if you come to a problem you have no idea how to do, it might be that you didn't read the handout before you started. So what answer do we get the logical, understandable way at the top? We multiply those numbers out. What do they multiply out to be?
15,120.
Now, what's 9 factorial as a number? 362,880. Now 5 factorial is 120, and 4 factorial is 24. So if you do this multiplication and division, you can compare it to the answer you got directly. Okay, so now I'm going to ask you to do, in any manner of your own choosing, number 16. Number 16. C25-4. Now for myself, not being masochistic, I make any cancellations I can before I multiply or divide. So let's see what numbers we produce. So Kaylee, what number did you produce?
12,650.
12,650, raise hand if we agreement. So that is the number we want to produce. Now let's do number 19. Number 19 is C73 over C54. So you have to do two combinations, and once you finish, you divide them. So calculate C73 on top, and calculate C54 on the bottom, and perform the division. So Casey, you have a final answer?
I got
7.
7, all in favor? We have support for 7. Does anyone want to see some steps?
Yes.
Okay, well, I'm gonna do some side work. Side work. C73 is equal to 7 times 6 times 5 over 3 times 2 times 1. And I see some cancellation there. The 3 and the 2 goes out with a 6 for a result of 35. So I have a 35 on the top. Now I'm going to do some more side work for the bottom. I have C54 is equal to 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1. And I also have some cancellations there. 4, 3, 2, 1 for a net of 5. So I get a 5 on the bottom. Now you have to divide 35 by 5 for a final answer of 7. Okay. Next problem, number 27. Again, it's a 3-piece problem. You have to do all 3 pieces. Okay. So here we are, number 27. We have C42. Then after we get that, we have to multiply it times C81, C61, and then we have to divide that by C18.3. So you have to do all 3 calculations in side work. In side work, you do all 3 calculations. Again, you're gonna have to read the pages before you do the problems. You guys are coming up with good answers. So Stephanie, your final answer is
3/68.
3/68. Let's see if we get some support. Kaylee, your answer is, sorry please,
0.044.
.044?
Yes.
You got decimals, huh? You didn't get a simple fraction.
You just divided 36 by 8/16. It's the same.
Same, same?
It's the same, yes, sir.
Same,
It's just
same.
whether or not a decimal or you wanted it in a fraction
That's true.
form.
No, a simple fraction like this we'll leave alone, but it's understandable, decimal's acceptable. Anyone like to see Stephanie work it out? Oh, we have a yes, so Stephanie, could you go through some steps?
No, it's okay.
Oh, she said that's okay.
Do you wanna
I
take
wanna
a,
do it.
you wanna see it?
Huh?
After
I
class.
can look at it later.
Yeah, okay, good, thank you, that handles that. Now, why are we doing all this? I just taught you how to count. Because if you do a classical calculation of probability, I should have shown you this before.
Thank you.
But you calculate classical probability as the number of favorable cases, this is very important. Over the number of total cases. And all we've done for the last hour and a half is pause in our development of probabilities to find shortcut counting methods for number of favorable cases and number of total cases. We've developed the fundamental counting principle, we've developed permutations and combinations, and all three of those are only used to calculate either your denominator or your numerator. They're counting techniques, nothing else. Now we're going to go back to probability. So let's go to the Xerox pages near the end and look at a problem of my choosing, if I can find one that I want, or else I'll go to the textbook. So I'm going to go to page 188, 189, number 24. So that's a challenge, harder than anything we've done in the class. I'm going to go to page 189, number 24. So let me know if you found it. It says, if two die or rolled, two die or rolled, two die or rolled, find the probability of getting a sum of 6, or a sum of 7, or 11. A sum of 6 or 7 or 8. Okay? So, the way I'm going to attack this problem, I should have shown you this earlier. The probability of A is the number of favorable cases over the number of total cases. cases. This is important. Now I'm gonna do something that we couldn't have done 2 hours ago, and I'm going to develop the number of total cases for 2 die. Here I have a red die. What color is this red die, Freddie? What color is this red die? It's red, okay? Now when I drop it, how many different numbers can come on top? 6. For each one of those 6, it can be matched with how many choices for the blue die?
Third.
It's under blank,
This round, next up.
It's
From that, right.
Spend your name with the card.
I know. Should've done the blue one first. Okay, now, for each one of these 6 that the red can assume, it can be partnered with how many final choices for the blue? 6 for a total selection of how many for the 2 die?
About 6.
36, agreed? Fundamental rule of counting. The number of ways you can do the first thing times the number of ways you can do the second thing, agreed? 36. Now, these 36 different possibilities are easy to understand, but if you prefer to have them out as a table for you, then they've been written out as a table for you. And the page in your handout that has that particular table is page getting close. Getting very close. Page 628 in the upper left. You have a table of all the different results you can get with 2 die. Agreed? But I maintain you don't need to use this table, you can just think about it a little bit. So let's go back to our reference question, page 189, number 24. First, it's going to be harder than I thought. Alright. Okay, a sum of 6 or 7 or 8. First, how many different ways can I form a sum of 6? I'm going to maintain I can have the following: a 1 and a 5, agreed? How about a 5 and a 1? A 1 on the red, a 5 on the blue, or a 5 on the red and a 1 on the blue? How about a 4 and a 2? And how about a 2 and a 4? Are there any others?
3.
3 and a 3. Now how many ways can I form a 7? I have a 6 and a 1, or 1 and a 6, 5 and a 2, 2 and a 5, 4 and a 3, 3 and a 4. Are there any others? So how many ways can I form an 8? What would they be? 6 and 2, 2 and 6, 3 and 5, 5 and 3, 4 and 4. True? Now, any one of these ways on the board is favorable to being either a sum of 6, or a sum of 7, or a sum of 8, agreed? So how many different favorable cases do we have? Count them up. 18. So it's equal to the number of favorable cases over the number of total cases, and we agreed the number of total cases was 36. So a probability of 1/2. Now let's go to a slightly easier problem. which goes back to, back to a page that doesn't even seem to have a number on it, so it's pretty bad. So I'm just gonna tell it to you. Now, in the actual game of craps that's played with 2 die, if you roll a 7 or 11, you are a winner. So what's the probability of rolling either a 7 or 11 on your first roll? Well, how many ways can you get a 7? And how many ways can you get an 11? How many ways can you get a 7? 6. We did that. 1 times 6, 6 times 1, 2 times 5, 5 times 2, 3 times 4, and 4 times 3. So how many ways can you get an 11? Tell me what they are.
5 and 6, 6 and 5. Just kidding.
You gotta write them down. So we have a total of how many favorable cases? 8. 8 over total of denominator is 36. So 8 over 36 is the answer to the problem. Good. So the next such question is, and this will be our go home problem. We want a sum less than 4 or greater than 9. A sum less than 4 or greater than 9. I want to know the probability of producing this with 2 die. A sum less than 4 or greater than 9. And this will be our go home problem. Or greater than 9. Tony's gonna take us through that door and out. I hear what we,
1/6.
I'm going home on her shoulders. Tony, the answer is?
2 nights.
Stay here. Unless I'm wrong. Any support for her answer? Less than 4, greater than 9.
I got 1/6.
1/3.
What a bunch of individualists. Can't any of you get the same answer? And it's not even my answer.
Oh, we're all wrong?
I don't know if you're wrong or not, because I'm not infallible, as we well know.
Oh, I'm so. I got
Yeah, it's all
11.
right, apology accepted.
I got 11 over 36. I also got 1/6.
I got 12 over 36.
1 plus 1, 2
This
plus
could
1,
be a while.
1 plus 2.
There's
Could be
2
a
of each
while.
of those though, there's 2 die. And if you have 2 different colored die, right, and
I'm staying on my answer.
So,
I'm sticking
One
on
and
my
one.
to
answer.
get less than, less than 4, so it's 1 and 1.
right, there's 0 for the first one, 0 for 1, there's no way
We
you
don't
can get
have
1
zero.
rolling 2 die. Right, and then 2 1 and 1s for 2, and then a 1 and a 2 and a 2 and a 1, right?
That makes how many so far?
3.
4.
3. Why 4?
And 1 and 1, 1 and 1.
You don't count that one twice.
That's 1.
When he,
Oh.
when
One
he
on the
wrote it up
blue
on
and
the
one
board,
on
he
the red.
never,
Screwed up.
he never
That's
counted
one.
those twice.
One on the
that's-
blue and one on the red is the same as
I
one
was
on the
doing
blue
my
and
math
one on the
wrong.
red.
Right.
And then greater than 9 is 6 and 4, 4 and 6.
I was
Uh,
wrong.
6 and 4
No,
I
Right.
didn't do that.
5 and 6, 6 and 5.
right?
And 6 and 6.
For a total of how many?
1, 2, 3.
9.
9 over 36, yes.
Go home.
Yes.
My bad.
9 over 36.
I thought that that's what you said.
I said 1 6, what, does it equal
9 over
1 6?
36
I
is
wrote
not
6 over
1 6.
36.
Oh. No, it's
Yeah,
One
no.
fourth.
Yeah, it's 1
I heard-
4th, 1
not.
4th.
I heard something different.
I said 1 6, what did you ended up, what did you
Well,
say?
Wow.
You
we
said
were out
1
of here
4th?
2 minutes early.
Did you say 1 6?
No.
No.
So there's a couple of people said 1 6.
9 over
I said
You
8
said
over
9.
36 because I was forgetting about 1 and 1.
Got it.
Got it.
Okay, so 1.
Okay. Okay, we
Oh my God.
we did it.
That was hard.
Now, when we come in on Thursday, we're gonna go over this assignment. And immediately going over this assignment, we're gonna test on A1 through A4.
Study groups? Which one did you want to see? This one, 47? White House?
Working,
Kentucky? What times are you
working,
here, like,
so unless you
between-
wanna do it at midnight.
Negative now and.
I don't get off work till 10:30 at night, so unless you wanna do it at midnight.
From 11 to 12 in the morning. And I'm usually
But you
here
don't have
from
curfew either,
2 until
so.
4 in the
No, I do
afternoon.
not, because I am a
Okay.
civilian.
Not guaranteed,
And
but
we do
usually every
glorious.
day, usually.
Okay, for some reason, the
Actually, I do have
factorial
curfew.
thing is not, it's not sinking
Apex
in, but I think I
employees
just
have
need
to
to
be
go home
out
and
bars and
go
stuff
over
by
it.
midnight.
But in case not, I wanna know, but I just.
Absolutely.
Nope,
Okay.
done.
What?
We are done drinking at midnight.
Working for APs, I'm sorry, APs is wonderful, for APs.
It is there were problems and incidents and drunk driving and, yeah, not here, but, and so, well,
Like,
Chapter 4 is a
same thing, that's military,
Chapter
that's,
4 is a
curfew
duty.
here is because of.
I can't hear you, but there's
What-
a thing
not
on
just
the-
Okinawa, Tokyo too. I've been here for 8 years, I'm well aware. I'm well aware.
No, it was not fun during that time.
You got here in 2009, or
Same as me.
the end of 8.
9.
What month did you get here?
Okay, for
Okay.
those, study
Oh, do you have
groups.
my marker? The black one?
Did they still have it? No, they didn't have the green card,
Oh,
red
I was
card
like,
still
oh,
here, did they?
Did you
Okay,
put
so
this on
you
the board?
remember that.
No, not that
Red card.
one. Red card.
I didn't get one.
I was
I don't
18.
even-
I definitely had a red card.
Did you still have my marker?
Oh, you were only 18? Oh, do I have your marker?
What do you mean only 18? That's derogatory.
Here you go, I'm sorry. My bad. I do that consciously.
Yeah, I can do it.
Okay, so, only 18.
I'll be,
So we get more.
Oh, yeah, yeah.
Not even joking.
So you made it, how did you, what did you use?
Go for it, I made them, I brought these in for you guys, I thought more people would eat them. I made 2 trays of them.
What cocoa did you use? Cause that's really good. Cause I've ordered the Ghirardelli, like regular just plain cocoa, cause I don't like to use Hershey's chocolate. Like the
This
Hershey's
is some
cocoa.
Japanese brand, bricks of chocolate for doing this.
That was from this morning and I was.
It is meant to go in the double boiler, well, it's probably meant to go in a boiler pot,
Apologize
but I use a double boiler, and then I got my chocolate forms from Daiso over the years, cause I do this every once in a while.
Yeah.